Continuing with the previous lecture, today we are going to set up an equation of motion for the matter. Let's consider that the wave function can be expressed as a function of position and time. So let's take that it is traveling in positive x direction. Then the wave function capital psi is equal to a constant a into exponential I kx minus omega t, where k is the wave vector given as 2 pi by lambda, the lambda being the wavelength of the wave, x is the position, omega is the angular frequency, that is 2 pi into natural frequency nu, and t is the time. The reason we have written e to the power of I multiplied by some function of x and t is that the wave function is now a complex function. It's not a real function. It has both the real and the imaginary terms. Now, moving on, what I'm going to do next is take if I multiply this and take the product out, it will be a to the power of I kx into e to the power of I minus I omega t. So I'm going to write a e to the power of I kx as another function small psi, and the left over will be e to the power of minus I omega t. In the next step, I'm going to differentiate capital psi with respect to x and then with respect to t multiple times. So differentiating twice with respect to x, I will get d square capital psi by dx square is equal to e to the power of minus I omega t into d square small psi by dx square, because it's only small psi which is depending on x. If I differentiate with respect to time, I will get d square capital psi by dt square is equal to minus omega square e to the power of minus I omega t into small psi. Psi was independent of time, so it was only e to the power of minus I omega t, which I have to differentiate. So students who are watching this lecture, I would request them to write down first d psi by dt and then do d square psi by dt square, else you're bound to make mistakes. So with these expressions, let's see how we can come up with the Schrodinger equation or the equation of motion. So for that, I'm going to consider that this wave is now traveling. It's a traveling wave motion with a displacement. Suppose there is a traveling wave which is having a displacement y and velocity v in general, then d square y by dx square is equal to 1 by v square d square y by dt square. Applying it to the case of the wave function which we are considering for the particle, I can write d square capital psi by dx square is equal to 1 by v square d square capital psi by dt square. Let me substitute for d square psi by dx square and d square psi by dt square from the previous expressions which I have got. It now becomes e to the power of minus I omega t d square small psi by dx square is equal to 1 by v square into minus omega square e to the power of minus I omega t into small psi. We have e to the power of minus I omega t common on both the sides, that get cancelled. So the next, we can write it as d square small psi by dx square is equal to minus omega square by v square into small psi. A main point to be noted is that we have got rid of the term which has a dependency on time. So this equation now is a function of only position. Next, let me take the expression for omega and velocity. So omega is given as 2 pi into nu being the frequency. Velocity is equal to product of frequency and wavelength, so v is equal to nu into lambda. Substituting for omega and v, I can write d square small psi by dx square as minus 4 pi square by lambda square into small psi. The next step, I will just rewrite this expression and get 1 by lambda square. So if I want 1 by lambda square, this entire minus 4 pi square side goes to the left hand side and remains in the denominator. So it becomes 1 by lambda square is equal to minus 1 by 4 pi square small psi into d square psi by dx square. Why did I do this? Why did I get an expression for 1 by lambda square? Let's figure it out. So here comes a reason. I'm going to consider that this particle is having a mass m and it is moving with a velocity v. Then its kinetic energy will be given by half mv square. Or in terms of momentum, I can write it as p squared by 2m. But momentum, you can get an expression for momentum in terms of wavelength when you apply the de Broglie expression. So P is equal to h by lambda, or kinetic energy now becomes 1 by 2m into h square by lambda square, or h square by 2m into 1 by lambda square. Now, if I know the potential energy of the particle, which let's assume it as equivalent to a function of x, it is a function of x, so V, let's take it as V. Then if I add the potential energy with the kinetic energy, I will get the total energy of the particle. Let me substitute for kinetic energy and the potential energy. Then I can get total energy E as, so kinetic energy is h squared by 2m into 1 by lambda square. So h squared by 2m into this entire expression minus 1 by 4 pi square psi d square by dx square. That becomes minus h squared by 8 pi square m 1 by psi d square psi by dx square plus the potential energy V. In the next steps, all I'm going to do is just do a rearrangement here and get an expression for d square psi by dx square. I'll get it as minus 8 pi square m by h square into e minus v into psi. Let me just rewrite it in another way, or bring this right hand side term to the left hand side and write it as an equation like d square psi by dx square plus 8 pi square m by h square into e minus v into psi is equal to 0. Now h, the Planck's constant, can be given as 2 pi into h cross. This is, we usually write it as h with a horizontal bar, but pronounced as h cross. So if I substitute for h as 2 pi h cross, I can rewrite this entire equation as d square psi by dx square plus 2m by h cross square into e minus v into psi is equal to 0. These two expressions, or these two equations, are known as the Schrodinger equation in one dimension, which is time independent. Very important equation, and it has a wide variety of applications. So we can see that what are the different terms. The wave function obviously will be the solution. If I solve this equation, I can get the wave function. If I know what is V, that means what is a function of this potential energy, how does the potential energy is, and then if I know the mass of the particle, if I solve this, I know that it will be valid only for a particular value of energy. Energy value will be a discrete quantity. So for any value of energy, I will get a wave function. Another value of energy, I'll get another wave function. So each of these will be a discrete. Now, the values of energy for which these equations are valid, the Schrodinger equations are valid, are known as eigenvalues. And the solutions of the Schrodinger equation, that is a wave function, are known as eigenfunctions. In the next lecture, we will make use of the time-independent Schrodinger equation in one dimension and try to explain two conditions. That is, one, when the particle is free to move, and another one when the particle is confined, that is, there are some boundaries, it is existing within a boundary.